Hey there, we're going to go over some dynamic torque notes and work a couple problems together. In our last video, we introduced the concept of torque and seen where torque was a measure of how a force acting on some object causes that object to rotate. And then we worked on making our net torque equations. And we've seen where there was a lot of similarities in our forces, our static forces unit, and that static torque. And now what we're going to get into is our net torque is no longer going to equal zero. And in these cases, when this happens and we do have some kind of a net torque, that object will start to experience an angular acceleration. And this was just like in our forces unit, whenever we had a net force of zero, there was no acceleration. And then once we did have a net force, we started having a acceleration. And that's whenever we introduced Newton's second law, and we said that the acceleration of the object was equal to the net force divided by the mass. Well, we have a similar expression for our angular acceleration, and it's equal to our net torque. So instead of forces, it's a net torque divided by, now it's not just the mass, it's how the mass is distributed. And we use a letter I, and that stands for rotational inertia. Now, you may hear me say moment of inertia sometimes, and it's the same thing. Some people refer to it as moment of inertia, others rotational inertia, but it's the same thing. And let's take a look at that. We have rotational inertia, and that's a letter I, a symbol I that we use. And again, it's just how that mass is distributed. So last class, we kind of looked at an example, and I had that wheel, and on that wheel there was these four different spokes, and at the edge of each one we had the little disc, and we hooked up a hanging mass that was connected to the center of that, and when we released it, it started spinning. And we kind of observed it spinning, and then what we did is we got those four discs and we moved them towards the center, closer to that axis of rotation. So then we had something like this. And by doing that, we were changing the rotational inertia. In other words, how that mass was distributed. Over here in the first case, the mass was further away from this axis of rotation. And then when we moved them in, we moved them closer to that axis of rotation. So we were changing how the mass of that object was distributed. And then whenever we released that hanging mass the second time and it started going, it rotated faster. And the reason why is because now the mass was distributed closer to our axis of rotation. So the general rule of thumb here is that the farther away from the axis of rotation, it results in a greater rotational inertia. And so we have these different equations, and it just changes depending on the shape of the object. And some of the common shapes that you'll kind of deal with are a hoop, a solid cylinder or a disc, a solid sphere, a rod where the axis of rotation is at the end, or a rod where the axis of rotation is there towards the center. And we have these different expressions for the rotational inertia. Now, you don't have to memorize these, and they're not written on the equation chart, but on your actual questions on the AP exam, they're either going to give you this expression for that particular object, or they're just going to tell you I equals blank, whatever that rotational inertia is. So you don't have to memorize them, you don't have to look for them on the chart. They're going to be provided for you, or the magnitude of that I will be given to you as well. And so now what we're going to do is we're going to kind of look and practice a problem using these concepts of moment of inertia to calculate the angular acceleration of an object. So for this first one here, we have, it says the mass of the object below is 0.5 kilograms. The length of this rod is 0.8 meters, and we're asked to calculate that angular acceleration of the object. So this 0.4 meters, that's that R here, and the 0.2, that's R for this force over here. So let's go ahead and just label this. Let's say this is force 1 and this is force 2. Our starting point is to make our net torque equation. Now don't forget, you usually want to draw in your FG here, but since the axis of rotation is at the center, the R is equal to, the moment arm is equal to 0, so there's no torque being caused from this gravitational force. Okay, so we can kind of ignore that one. So let's build our net torque equation like we did last time. So the net torque on this object is going to equal, so this first force, we'll call that F1. It's pushing up on the object, so it's going to cause it to rotate counterclockwise. That means it's going to be positive. We'll call this other force here F2. It's pushing up on it, so it's going to cause it to rotate clockwise. That's going to be my negative one. So in my net torque equation, it's going to be the torque caused from that first force minus the torque caused from that second force. Now we don't know if it's equal to 0 here, and so there's my net torque equation. And the next step is to now substitute, remember torque is equal to R, that moment arm, times your force. So we're going to plug that in here to our equation. So my net torque is equal to that force F1 times its moment arm minus F2 times its moment arm. Now we know all these values, so we can go ahead and plug those in. So my net torque is going to equal 100 newtons times that moment arm, which is 0.2 meters, minus, we have F2, which is 25 newtons, times that moment arm, which is 0.4 meters. So we can plug these values in, and when we do, we see that our net torque is now equal to 10 Newton meters. So we do have a net torque here, so we will experience an angular acceleration. So the next step is to find that rotational inertia, that I value. And so looking at this, okay, we have this rod that's fixed at the center. So we would go to this little chart here, and it's going to be this one right here. And so to calculate the I, we're going to use this expression. I equals 1/12 the mass times the length squared. So let's go ahead and write that down here. 1/12 ml squared. So we can plug in our values. The mass was equal to 0.5 kilograms and the length was 0.8 meters. So we got 0.5 kilograms, 0.8 meters, and that's squared. So the moment of inertia for this object here, for this rod rotating around the center, is equal to 0.027 kilograms times meters squared. So there's my rotational inertia. So now we know the net torque and we know the rotational inertia, so we can solve for that angular acceleration. So my angular acceleration is equal to my net torque divided by that rotational inertia. So we can plug in our values. We have 10 Newton meters divided by 0.027 kilograms times meters squared. And we end up with about 370.4 radians per second squared. So there's my angular acceleration for this object here. Let's look at another example. This one says we have a wheel, which is basically a solid cylinder, has a radius of 0.2, mass of 6 kilograms, and then we have a 4 Newton force applied to the edge that's perpendicular to the radius. So first off, let's just kind of draw what's going on here. So we'll draw our wheel. There we go. And then attached to the edge, we have some kind of a force that's perpendicular to it. Now we do have Fg right here at the center. But again, the moment arm is equal to 0, so the torque caused from the weight of this is just equal to 0. So we can kind of ignore the Fg there. Let's start out, let's make our net torque equation. So my net torque is going to equal, we have this force here, so torque from that F1, and then that's the only thing that's causing torque on this. So we can plug in and we can solve for our net torque. It's going to be the moment arm times that force, and the moment arm is just going to be the distance from here to here, which is the radius. And then for our force, it told us in the problem that it's 4 newtons. So I got 0.2, which is that radius or that moment arm, times 4 newtons. So my net torque is just equal to 0.8 Newton meters. Now we're looking for the angular acceleration, so we need to know what the rotational inertia is equal to. So it said a solid cylinder. Let's go up to those common shapes that we have. We'll find our solid cylinder, and it's going to be this one here. I equals 1/2 mr squared. So we can come back here, and we can say 1/2 mr squared. So we can plug in the mass, which is 6 kilograms, and the radius squared, so 0.2, and then that's going to be squared. So my moment of inertia, or my rotational inertia, is going to equal about 0.12 kilograms times meters squared. So now we have our net torque, and we have our rotational inertia, so we can solve for that angular acceleration. Angular acceleration will be our net torque divided by rotational inertia. So we can plug in our values. We get 0.8 Newton meters divided by 0.12 kilograms times meters squared. And when we plug that in, we should get an angular acceleration of about 6.7 radians per second squared. So that's how we solve for the angular acceleration using the net torque and moment of inertia or rotational inertia. It's very similar to our forces unit. Okay, so you want to kind of do the whole process similar to what we did in the forces unit. You look at the forces acting on the object. From there, build your net torque equation. Then you can solve for your net torque. And then lastly, you want to solve for your rotational inertia, depending on the shape. Now remember, you don't have to memorize these. On most questions, they'll either tell you what the equation is, or they're going to tell you what the actual rotational inertia is.